Now, in previous lecture, we discussed that the spectrum of compact linear operator, which is a countable, and 0 is the only limit point of sigma of t. Sigma of t is the spectrum of compact linear operator. Now, our next result is if t from n to n, if t from n to n, compact linear operator, and S is from n to n bounded linear operator, right? T from n to n compact linear operator and S from n to n bounded linear operator, then show that TS and ST, these are compact operator, right? That is our purpose. Now, this is norm space, this is a norm space, and this is norm space. So this is mapping T, which is a compact linear operator, and this is a S, which is a bounded linear operator, right? Then the composite mapping, which is ST, that is from n to n. So that is a composite mapping. Our purpose is to prove this ST is a compact linear operator. In order to prove ST is a compact linear operator, we take some bounded sequence from this set, from this domain, then its image in this n, which has convergent subsequence. If it has convergent subsequence, then this operator is a bounded, right? Now, if we take, suppose in this we take let Pn, which is a bounded sequence in n, right? Now this T is a compact linear operator. Then it means by definition of compact linear operator, its image has convergent subsequence. It means TPn has convergent subsequence. Suppose that is a TPnk. So this is a convergent subsequence, right? Now this S is a bounded operator, bounded or continuous. We can say that S may be bounded and continuous. Then in that case, if it is a continuous operator, continuous function, in that case, if mapping is continuous, then its image converge to its image, right? So in that case, ST, P and K converge to SP. Then what is this? This is a sequence in N. So what is ST, P and K? This is a subsequence. This is a subsequence under this image. Under this image, it means the image of this sequence under ST has convergent subsequence. If it has convergent subsequence, then this operator is a compact linear operator. So that is our first part. Now second part, S is bounded and T is compact. Then the composite function is Ts from n to n, right? Now again we take some bounded set in n. Now we are not taking sequence, now we are taking set. Let A be a bounded set in n, right? Because it is bounded, then its image SA is again bounded set in n, right? So this is a bounded set in n. If it is a bounded set in n and T is a compact operator, then the image of a bounded set is relatively compact under T. So its image, that is T of SA, is relatively compact. If it is a relatively compact, so we take any bounded subset in this set, and its image under TS is relatively compact, then it means that TS is a compact linear operator. So in both the cases, ST and TS both are the compact operator, right? So what we get? We get if T is a compact operator and S is bounded operator, then composite map TS is also compact operator and composite map ST is also a compact operator. Now next is very important result. This is now T from N to N be a compact linear operator. So first point is given. It is a compact linear operator from same space. Then the null space of T lambda. So first what is T lambda? T lambda is T minus lambda I. So nullity of T lambda, all element of N whose image under T lambda is equal to 0. So this null space is a finite dimensional, right? So this null space is a finite dimension. So in order to prove this result, we use this theorem. What is this theorem? So that we can check from the function analysis by Erwin, Kreyszig and many other book of function analysis. If a normed space N has property that closed unit ball, this is closed unit ball, is compact, then dimension of nullity of T lambda is less than infinity. In that case, dimension of operator is less than infinity. It means it is a finite dimension, right? So if any space has the property that every closed unit ball is compact, then the dimension of nullity is finite. So we use this result. Now, in order to prove this theorem, we use this result. So remember that if every closed unit ball is compact, of N is compact, then dimension of nullity of T lambda is less than infinity, or it is a finite dimension. Now, first we consider U set, which is X belongs to nullity of T lambda such that norm of X less than equal to 1. So this is a closed unit ball in a nullity of T lambda, right? So this is equation number 1. Now, if we take some sequence from this U, then it satisfies two conditions. One, its image under T lambda is 0. Second, norm of this is less than equal to 1. So Pn be sequence in this. So it satisfies this condition, number 1. Second is its image under T lambda is 0, right? So norm of Pn less than 1 means this sequence is bounded. If this sequence is bounded, then we can use the definition of compact linear operator. Since T is a compact linear operator and this sequence is bounded in N, then its image has a convergent subsequence, right? So its image has convergent subsequence. So we can say that its image TPN and it has convergent subsequence. Suppose it converges to Q. That is by using definition of compact linear operator. Again, Pn belongs to nullity of T lambda, then its image under T lambda equal to 0. So what is T lambda? Which is T minus lambda I, which is equal to 0. So what is this? This is a Tpn minus lambda Pn equal to 0. So it implies Tpn is equal to lambda Pn for every n, right? So this is the eigenvalue of T. Now, if since this lambda is non-zero, that is given in the theorem. Since lambda is non-zero, so this Pn can be written as lambda inverse Tpn, right? Similarly, this Pnk can be written as lambda inverse Tpnk. Now we know that this sequence is convergent. Then its scalar multiplication is also convergent. Okay, so right hand side is convergent, then it means left hand side is convergent. So what is this? It is a subsequence of Pn. So this Pnk, it means converge to P belongs to U. Why this P belongs to U? Because U is closed. So this is a limit point. Since U is closed, so P belongs to U. So this sequence converges to P and P belongs to U. Now every sequence Pn in U has a convergent subsequence. We prove that every sequence Pn in U has convergent subsequence. Then it means U is compact. If U is compact, then dimension of nullity of T lambda by that theorem is finite. If it is finite, then nullity of T lambda is a finite dimensional space. So this is very important result. So remember, if T is a compact operator, then its nullity is finite dimensional. Similarly, we will prove later on its range is closed, but nullity is finite dimensional. In addition to this theorem, remember this: nullity of T0 contained in nullity of T1 and so on up to infinity. This is 0 and so on up to infinity, right? So first this is equal to 0. So what is nullity of T0? So by definition of T lambda, what is this? This is a T minus lambda I, right? When T0, then T0 is I minus lambda I. So this values from this, it consisting only 0 elements. No, that is trivial. It consists only 0 elements. Second result is T1 is contained in T2. Yeah, we may in general say that Tn is contained in Tn plus 1. Thus, nullity of Tn is contained in nullity of Tn plus 1. In order to prove, we take some vector from this and that belongs to this set. If we take x belongs to this set, nullity of T lambda n, then what is by definition? By definition, T lambda n x is equal to 0. So what do you mean by this? It means the definition of this Tn lambda, which is Tn minus lambda I, x equal to 0. Our purpose is for n plus 1. So this is can be written as in this form, right? So what is the value of this? This is 0. If this is 0, then this is 0. So it means this value is 0. X belongs to nullity of T lambda n plus 1. So this is a subset of these values for n, 0, 1, 2 and so on. So what we get? We get this 0 is equal to nullity of T0 lambda contained in nullity of T1 lambda and contained in nullity of T2 lambda. So this result is very important. What is the result? In compact linear operator, the nullity of T lambda is finite dimensional. Also, in addition to that result, it also proves this result. Now, in next theorem, in compact linear operator, the range of T lambda is closed. That we will discuss in the next lecture. So what we get? We get in compact linear operator, the nullity is finite dimensional and the range is closed. So these are the two basic result of the this compact operator, and we can also say that it is a property of compact linear operators.